You know exactly why you are here. You aren't tuning in to memorize like a dry list of facts just to pass a multiple choice test. You are here because you want to build flawless technical articulation.
Right. Which is the ultimate goal, really.
Exactly. You want to walk into your next meeting or sit down for that major interview and sound like a seasoned pro who truly understands how the digital world is wired together.
Yeah, because knowing what an acronym stands for might win you a trivia game, you know? But being able to confidently explain how these technologies interact, why they fail, and how to fix them, I mean, that is what separates a novice from an expert. Knowledge is really only powerful when you can actually articulate it to someone else.
So today we are taking a deep dive into a massive stack of material.
But we are completely throwing out the quiz format.
Oh, 100%. Instead, we are weaving every single concept into this cohesive, high-speed articulation masterclass. We're going to trace the entire journey of a digital system.
Right, from the ground up.
Yeah. We'll start at the physical network cables, move up into the operating system, figure out how to lock down the data, build a human defense framework around it, and finally, analyze the attacks themselves. Ready? Let's unpack this.
Let's do it. So, to articulate how to secure a system, you fundamentally have to explain how systems talk to each other in the first place. That is the bedrock of everything we do.
Right, and whenever I look at network architecture, I hit a wall with the two big models, the OSI model and the TCP/IP model.
Yeah, the classic comparison.
Right. I always hear people compare the OSI model, which was defined by the International Organization for Standardization, to a postal service, and it has 7 distinct layers.
Which is a lot to remember.
It is. Meanwhile, the TCP/IP model only has 4 layers: network access, internet transport, and application. So why do we even need 2 different models to describe the exact same internet?
Well, it really comes down to theory versus reality. The TCP/IP model is practical. It perfectly mirrors how network engineers actually built the internet to function. But the OSI model is highly detailed and theoretical, which makes it the ultimate troubleshooting tool. Let's actually build out your postal service analogy to see how it works in practice.
Okay, I'm tracking. Let's hear it.
So at the very bottom, layer 1 is the physical layer. This is the physical road the mail truck drives on, transferring raw data as binary bits, using 2 modes, baseband and broadband.
Right.
Above that, layer 2 is the data link layer. This is the local mail truck itself, using MC addresses to move data frames around your specific neighborhood or local network. But if you want to send a letter to another city,
you need layer 3, the network layer. So layer 3 would basically be the ZIP code on the envelope.
Spot on. Layer 3 handles routing moving packets across entirely different networks using IP rules. And when that massive package hits layer 4, the transport layer, it handles segmentation.
Oh, so it breaks that massive file down into manageable pieces so it can actually fit on the trucks.
Exactly. Which brings us to the session layer at layer 5.
I've always found this one interesting. Why is the session layer so crucial for reliability?
Think of it as the ultimate checkpoint system, It establishes, maintains, and terminates the connection.
Right.
But practically, if you are downloading a massive system update and your network drops at 99%, the layer 5 checkpoint ensures that when you reconnect, you resume from 99% rather than starting all over at 0.
That makes perfect sense. So we've got the roadmap of how data travels. But how do devices actually find each other? I mean, there is a fundamental difference between an IP and an IP address, right?
There is. IP, or Internet Protocol, is just the standard set of rules for routing. The IP address is the actual numerical label assigned to a device.
Right.
But human beings are notoriously terrible at remembering random strings of numbers.
Right.
Which is why we use DNS, the domain name system, to map easy-to-read domain names to those IP addresses.
And that mapping isn't just a simple one-to-one list. Depending on what you're routing, you need a different DNS record.
Exactly right. Like if you are mapping a domain to a classic IPv4 address, you use an A record. For the newer IPv6 addresses, you use an AAA record. Sometimes you just want to point one domain name to another domain name, which is called aliasing. And for that, you'd configure a CNAME record. Meanwhile, MX records strictly direct your email to the correct mail server.
And then you have the TXT record, which is vital for security, right?
Oh, absolutely. It stores verification text and email security policies like SPF and DKIM to mathematically prove that an email actually came from who it claims to be from.
So once we actually establish that connection and we hit the application layer, we need to secure the conversation. That's where HTTPS comes in, utilizing SSL/TLS for encryption. But just hiding the data isn't enough, right? We have to prove it wasn't tampered with in transit.
Right. And to do that, the system uses a MACM, a message authentication code, alongside AEAD, which stands for Authenticated Encryption with Associated Data.
Okay.
These ensure both the confidentiality and the integrity of the message. And broadly speaking, all these protocols we just discussed fall into three operational categories: communication, management, and security.
Okay, so we've explained how traffic moves and stays intact. But how do we act as the bouncer for a network? We don't want just anyone walking in.
Right. Definitely not.
So this is where we deploy virtual network appliances, which are essentially software versions of hardware devices like firewalls.
And depending on your architecture, you might deploy them in different locations,
Right.
Network-based firewalls protect the perimeter, host-based protect individual machines, and cloud-based protect virtual environments.
Right.
But the way they actually inspect traffic is what you really need to be able to articulate in a meeting.
Right, because you have stateless, stateful, and next-generation firewalls, or NGFWs. Like, if I'm explaining this, I'd say a stateless firewall is like a bouncer who checks your ID at the door but has zero memory.
Right.
If you walk out and walk back in 5 seconds later, he checks your ID all over again. He evaluates every single packet in total isolation.
That is a great way to put it. A stateful firewall, however, actually remembers the state of the connection. Once you're approved, it tracks the ongoing conversation.
But for a modern enterprise, you really need that next-generation firewall.
Yeah, NGFWs are the most secure because they operate all the way up at layer 7 of the OSI model. They perform deep packet inspection.
Meaning they don't just look at where the packet is going, they basically open the envelope and inspect the actual contents for malware.
Exactly. We also have proxies acting as middlemen. How do you clearly distinguish between a forward and a reverse proxy?
Well, it's all about who you are trying to hide. A forward proxy protects the client. It hides your internal employees from the wild internet. A reverse proxy protects the server. It sits in front of your web servers to handle incoming traffic, hiding your internal infrastructure from the outside world.
Perfect. And what about VPNs? Virtual private networks create encrypted tunnels, but setting them up isn't always straightforward.
Right. It totally depends on the scale. Organizations use remote access VPNs for, say, individual employees working from a coffee shop.
Right.
But if you want to connect an entire branch office in London to headquarters in New York, you use a site-to-site VPN.
And site-to-site is notoriously harder to manage. You are configuring complex routing rules on hardware at both geographic locations rather than just, installing a lightweight app on a laptop.
Yeah.
To manage that complexity at scale, modern networks often use SD-WAN software-defined wide area networks to intelligently route traffic across whatever connection happens to be fastest at that exact moment.
And regarding the VPN protocols driving that encryption, you've got IPsec, which is incredibly secure but notoriously heavy and complex to configure.
Yeah, it's a beast.
Compare that to WireGuard, which is the newer standard. It's much faster and built on an incredibly lean code base.
To truly control all this traffic, network engineers divide the infrastructure into zones. They use subnetting to logically divide a network at layer 3, using a system called CIDR, or classless interdomain routing.
And simultaneously, they use VLANs to divide the network down at layer 2.
Right. Together, they isolate traffic into uncontrolled zones, like the public-facing internet, and controlled zones, like a secure internal intranet or a DMZ.
But everything we just discussed assumes a physical wire connecting these zones. The moment you introduce wireless, like the IE 802.01 standard, which we all commonly know as Wi-Fi, you literally broadcast that traffic into thin air.
Which is incredibly risky.
Yeah, that's exactly how vulnerabilities happen, like the famous KRACK attack that compromised the WPA2 security protocol.
Exactly. The airwaves are inherently noisy and vulnerable.
So let's say the traffic navigates the Wi-Fi, passes the firewalls, and finally arrives at its destination. What happens when the physical machine actually wakes up to receive it?
It starts at the very foundation. The BIOS, or on modern systems, the URFI, which stands for Unified Extensible Firmware Interface.
Okay.
Its two main jobs are to initialize the physical hardware and then hand control over to the bootloader. The bootloader is what actually wakes up the operating system.
Though nowadays, that OS might not even live on physical hardware, right? It's likely virtualized. I know hypervisors come in two flavors, Type 1 and Type 2. What's the architectural difference there?
So Type 1 is bare metal. It is installed directly onto the hardware itself.
Yeah.
Type 2 is hosted, meaning it runs as an application on top of an existing OS, like running a virtual machine inside your Windows laptop.
Okay, I see.
Cloud service providers like AWS or Google Cloud exclusively use Type 1 hypervisors technologies like KVM, VMware ESXi, or Hyper-V, because installing directly on the hardware offers vastly better performance and much tighter security isolation.
But is that isolation perfect? Like, can malicious software break out of a virtual machine and infect the underlying hardware?
It is rare, but yes. It's called the VM escape attack. And this highlights exactly why cloud security relies on a shared responsibility model.
The provider secures the hypervisor and the physical data center, right?
Yeah, but you are responsible for securing the OS and the data you actually put inside it. When migrating to the cloud, teams use baseline images which are pre-configured, highly secure templates to spin up new machines safely.
Oh, that makes sense.
And to mathematically secure those systems, physical hardware uses a TPM, a trusted platform module chip. In a virtualized cloud environment, they emulate that hardware using VTPMs.
Okay, so let's talk about the operating system that powers the vast majority of that cloud infrastructure, Linux, developed by Linus Torvalds back in 1991. If I'm trying to sound like a pro in a meeting, how do I accurately articulate what Linux actually is?
The crucial distinction here is that Linux itself is technically just the kernel.
Okay.
The kernel is the core engine that talks directly to the hardware. The operating system is the complete package built around it. And a distribution, or distro, is a specific curated flavor of that OS.
Right, because the architecture actually has 5 distinct components: the hardware, the kernel, the shell, user utilities, and the graphical desktop environment.
Right. And the shell is the vital translator. It takes the commands you type and turns them into a language the kernel actually understands. This architecture gives us popular distributions like Debian, Fedora, CentOS, Kali, and Ubuntu, which remains the heavy favorite in cloud environments.
And installing software on Linux isn't like downloading a standard executable on Windows, right? You use package managers. Why are package managers so much more effective than simple installers?
Basically because they automatically track dependencies. If the software you want requires 3 other background libraries to function, the package manager goes and gets them for you.
Oh, nice.
On Debian-based systems, you use apt, the advanced package tool, with simple commands like apt install. On Red Hat systems, you use yum, the yellow dog updater modified.
Okay.
When you install a package, it typically scatters about 7 associated files across the system, placing libraries and dependencies in specific directories so they can be shared by other programs.
Which means navigating a Linux system requires understanding the standard FHS, the file system hierarchy standard, which honestly can look like alphabet soup at first.
You really can.
You have /etc for your configuration files, /bin for your essential command binaries, /mment for temporarily mounted file systems, and /me for temporary files. The actual user files live over in the /home directory.
So if you are an analyst investigating an incident, how are you actually navigating those directories from the command line interface?
Well, if I suspect an issue in a log file, I'm not opening a text editor. I can use the head command to read the first few lines of a file, maybe adding -n5 to specify exactly 5 lines.
Right.
Or I can use tail to monitor the very end of the file in real time. If the log is massive, I'll use less, which lets me scroll page by page without crashing my terminal by loading a gigabyte file into active memory.
And how do you find the log in the first place?
The find command is incredibly robust. If I know the exact name, I use -name. But if I'm not sure about capitalization, I use -inname to ignore case sensitivity.
Oh, that's handy.
I can even search by time. If I want to see files modified in the last 60 seconds, I use -min -1. If I want files older than a minute, I use +1.
To chain all these commands together, Linux relies heavily on the pipe command, represented by the vertical bar.
Oh, I love explaining the pipe command. Imagine a factory with 2 workers standing next to a conveyor belt. The first worker finishes their task and drops the output onto the belt.
Okay.
The second worker picks up that exact output and uses it as their raw starting material. In Linux, the pipe takes the output of your first command and feeds it seamlessly as the input for your second command.
That is the perfect analogy. And you have other basic manipulators too. The touch command creates a brand new empty file. If you want to push text into a file, you use echo.
But you have to be careful with that, right?
Yes. A single bracket will overwrite the entire file, while a double bracket safely appends the text to the bottom.
Good to know.
If you need to delete a directory and everything inside it, people often use arm-R, but a much safer, more targeted alternative is using the find command combined with the -delete flag to ensure you only remove what you intend to.
Now, how do we make sure an entry-level user can't just accidentally delete a critical system file?
By understanding permissions. Every file in Linux has 3 types of owners: the user who created it, the group it belongs to, and other, which means absolutely everyone else on the system.
Right.
The permissions themselves are read, write, and execute. They are represented by numbers 4 for read, 2 for write, and 1 for execute.
So instead of memorizing the math for a command like chmod 664, I can conceptually think about it as assigning rights. I can use the bashmod command to add or remove access. Sudo versus root is a big part of this too, right? Root is the absolute super user, but you are never supposed to log in directly as root? Why is that?
It goes down to accountability, specifically a concept called non-repudiation. If everyone logs in as root and someone accidentally deletes the database, the logs just say root did it.
So you have no idea which human being was at the keyboard.
Exactly. By requiring users to log in with their own accounts and use the sudo command to temporarily elevate their privileges, the system records exactly who executed the command. You cannot deny you did it. And the rules for who is allowed to use sudo are strictly kept in the /etc/sudoers file.
And speaking of users, when we manage them with userav or userdel, we often assign them to groups. But groups in Linux aren't like folders you drop users into. They are literally just text files like /etc/group containing a list of names.
Right.
And if you get stuck on any of this in the terminal, you can just type whatis for a quick one-line description of a command man to open the full manual, or apropos to search all the manuals for a specific keyword.
So we've secured the Linux kernel, established our directories, and locked down user permissions. But none of that matters if the actual data living inside those directories is vulnerable. How do we build a fortress around the data itself?
Which means looking at how we store it. Before modern databases, companies used traditional office suites, like massive spreadsheets. But they were horribly inefficient at handling complex concurrent relationships. So the industry evolved to relational databases.
Right. In a relational database, data is linked. You have a primary key, which uniquely identifies a specific row in a table, and you have a foreign key, which is a column that links back to a primary key in an entirely different table, creating a relationship.
Okay.
To talk to these databases, we use SQL. You have the standard SQL language, and then you have client-specific statements like PostgreSQL and MySQL. Think of them as different regional dialects of the same core language.
When an analyst actually writes a query, the syntax really matters. Select chooses the column you want to view, while order by sorts the results. The where clause is your filter. But there's a huge difference between using an equal sign and using the like operator.
Oh, yeah.
If I query where destination IP equals 10.25.199.26, the database demands an exact perfect match. But if I use like with a wildcard % sign, like 10%, it will pull up every single IP address that simply starts with 10.
You also have operators like between, which is inclusive, meaning it grabs the start and end values as well as everything in the middle. The NL operator identifies fields that are entirely empty, not zero, but truly blank.
Right.
Describe will show you the structural blueprint of a table. And if you need to merge data from two tables, an inner join doesn't permanently alter the database. It just creates a temporary combined view for you to analyze.
Security analysts use this all the time. They will often capture network traffic using a tool like Wireshark, export that packet capture as a CSV file, and import it directly into a SQL database so they can run these complex queries to hunt down an attacker.
But query languages only help you organize the data. To protect it, we rely on cryptography. The foundational split here is symmetric versus asymmetric encryption.
Okay, let's break that down.
Symmetric uses the exact same key to lock and unlock the data historical algorithms like DES, its Upgrade 3 DES, and the modern gold standard AES. Asymmetric encryption, however, uses a math-based pair, a public key to lock it, and a private key to unlock it. You generate these keys using terminal tools like OpenSSL with commands like OpenSSL.
And the architecture that manages all these public keys across the internet is PKI, the public key infrastructure. It's essentially a two-step process: verify someone's identity and then securely exchange the information.
Right.
When a company wants to prove they own a website, they generate a CSR, a certificate signing request, to get a digital certificate. This solves the problem of credibility. But if their server gets hacked and that certificate is stolen, it immediately goes onto a CRL, a certificate revocation list, which alerts the whole internet to shift that certificate from trusted to untrusted.
We also need to draw a hard line between hashing and encryption. They are often confused, but serve entirely different purposes.
I always explain it like this: hashing is a digital fingerprint. If you run a file through a hash algorithm, you get a unique string of characters. It is completely one way. You cannot reverse engineer a fingerprint to build a clone of the person.
That's a great visual.
Encryption, on the other hand, is a safe. You lock the data inside, and as long as you have the key, you can open it up and pull the original data back out.
That's the crux of it. Hashes are about integrity. If malware alters even a single line of code in an update file, the resulting hash value will change completely, alerting you to the tampering.
Right.
But hashing algorithms can age poorly. The older MD5 algorithm is famously vulnerable to collation attacks, often called collision attacks, where two completely different files accidentally produce the exact same hash fingerprint.
Attackers also use rainbow tables, which are massive pre-computed databases of every possible password and its corresponding hash, allowing them to brute force leaked databases in seconds.
It's terrifyingly fast.
To counter this, security engineers use salting. They append random, meaningless data to your password before they hash it. This completely breaks the rainbow tables. They also use key derivation functions like PBKDF2 to mathematically stretch the password, making it exponentially harder to crack.
So we have the cryptography math figured out. But math alone isn't enough because human beings are messy. Organizations need rules. We need governance frameworks to manage who actually gets the keys to the safe.
The first thing to untangle here is the difference between security and privacy. Security is the technical barrier protecting the data from unauthorized access. Privacy is the legal and ethical framework dictating how you are allowed to use the data you collected.
Exactly.
We enforce this through security planning. You have policies, which are the high-level executive rules, standards, which are the mandatory technical requirements to meet those rules, and procedures, which are the step-by-step instructions for the IT team to implement them.
All of this planning revolves around calculating risk. The core formula is simple. Risk equals likelihood multiplied by impact. To understand your impact, you have to classify your assets.
Right.
The standard categories are public, internal only, confidential, and restricted. Restricted is the absolute highest tier, operating on a strict need-to-know basis. But classifying assets in the real world is a nightmare, because a single database might hold public marketing copy right next to restricted financial data.
To give organizations a blueprint, we use frameworks like the NIST Cybersecurity Framework, introduced back in 2014. It operates on three main components: core, tiers, and profiles.
Right.
The core originally featured 5 functions, but recently added a 6th. They are govern, identify, protect, detect, respond, and recover. Govern was added to ensure cybersecurity aligns directly with the organization's overarching risk strategy. But actually implementing NIST is notoriously difficult simply because the granular level of detail is so overwhelming.
And to prove you've implemented it correctly, organizations undergo security audits. Now, it's vital to distinguish between an assessment and an audit.
Oh yeah, big difference.
A security assessment is usually an internal, friendly evaluation of technical vulnerabilities. A security audit is a formal, independent, high-stress review of your entire process planning, field work, and reporting, often tied to legal compliance. When an audit finds a flaw, it goes directly into a risk register for tracking.
For active day-to-day defense, teams rely on playbooks like a specific incident response playbook for a ransomware outbreak. They coordinate this using a SIEM, security information, and event management.
Right.
Whether it's self-hosted on physical hardware, cloud-hosted, or a hybrid of both, a SIEM fundamentally exists to ingest massive amounts of log data from all over the network and analyze it in real time for threats.
But who is actually generating those logs? That brings us to Identity and Access Management, or IAM. You'll hear a lot of acronyms here, primarily AAA, MBC, and DAISY.
Let's ground that alphabet soup in a real-world scenario. Let's say you are managing access to a highly secure VIP building. How does AAA apply?
Well, authentication is the bouncer at the front door, checking your physical ID to prove you are who you say you are. Authorization is the bouncer checking the clipboard to see exactly which floors you are allowed to visit.
Okay.
Accounting is the network of security cameras quietly tracking every single room you enter, enforcing a segregation of duties and building an audit trail.
Perfect. And single sign-on, or SSO, means you only have to show your ID to that front desk bouncer once, and you get access to all your approved applications for the day.
Exactly.
Under the hood, this often relies on LDLP for directory lookups, SAML for securely passing your authentication data between different enterprise services, or Oath for granting token-based access to third-party apps without sharing your actual password.
So once you are authenticated, how does the system decide what files you can open? If the system uses discretionary access control, or DA, it means the human who created the file gets to decide who can read it. If it uses role-based access control, your job title, say HR manager, automatically determines your access.
Yeah.
But mandatory access control, or MAC, is the strictest model. It is completely non-discretionary.
The military uses that one heavily, right?
Yes. MPAN determines access strictly based on system-wide clearance levels. Even if you created the file, you cannot grant someone else access to it.
Which leads us to provisioning, granting access, and deprovisioning, revoking it when someone quits. We manage standard user accounts for humans, but we also provision service accounts, which are granted strictly to applications so they can perform automated background tasks.
Right.
And we have to closely monitor session IDs and cookies to prevent session hijacking, where an attacker literally steals your active login token mid-session and bypasses the bouncer entirely.
Even with the best bouncers, someone is going to try to break in. No framework is perfect, which brings us to the attack surface itself.
We need to define threat versus vulnerability. A threat is the actor or the event, whether it's a deliberate hacker or an unintentional power outage that could cause harm. The vulnerability is the actual technical flaw they exploit.
And migrating to the cloud has exponentially increased our digital attack surface compared to the old days of just securing a physical server room.
Oh, without a doubt.
To manage that surface, we use vulnerability scanners that look at every layer of our defense in-depth strategy. Right. When researchers find a new flaw, it gets added to the CVE list.
Which is the common vulnerabilities and exposures database managed by AMITRE, right?
Exactly. Specific organizations called CNAs are authorized to assign the actual CVE tracking numbers. The severity of the bug is scored by the CVSS system. Meanwhile, web developers constantly reference the OWASP top 10 list to ensure they aren't building those vulnerabilities into their code in the first place. Because ultimately, you cannot protect what you cannot see.
Let's look at the attacks striking those vulnerabilities. You have malware like Trojans, named after the wooden horse of Troy, which disguise malicious code inside legitimate-looking software.
Yeah.
You have sniffing, which happens down at layer 2 of the OSI model. Attackers set a network interface card to promiscuous mode, allowing it to silently intercept all traffic crossing the local network.
Then you have spoofing, which is falsifying your identity. In a classic Smurf attack, the attacker spoofs the victim's IP address and sends a massive wave of ICMP echo requests, basically ping messages out to a broadcast network.
Wow.
Every machine in the network replies to the victim simultaneously, instantly flooding and crashing their system.
That's a textbook DOS, or denial of service attack, designed to exhaust system resources. If you are analyzing network traffic and suddenly see a massive spike in TCP, RST, or reset flags, it's a huge red flag indicating either a port scan or an active DOS attack.
Right.
But sometimes attackers bypass the technology entirely using social engineering. A common physical tactic is piggybacking, where an attacker confidently tailgates an authorized employee right through a secure door. The only real patch for that is comprehensive employee training.
Phishing is the digital equivalent. Attackers use phishing toolkits, which are pre-packaged software bundles that deploy fake login pages and malicious attachments to harvest credentials.
And if they steal a hash password?
They might just pass the hash, submitting the hash directly to the authentication server to gain access without ever needing to crack the plaintext password.
That's wild.
If they do need to crack it, a dictionary attack throws millions of known passwords against a single user's account. A reverse brute force attack flips the script. It takes one incredibly common password and tries it against millions of different usernames to see who was lazy.
On the web application side, we deal with cross-site scripting, or XSS. Reflected XSS bounces a malicious script off a vulnerable web server directly to the victim's browser. Stored XSS is worse. The script is permanently saved on the target server, infecting anyone who visits the page.
Right.
DOM-based XSS executes entirely locally within the victim's browser environment.
And we can't forget SQL ingestion, where attackers manipulate database inputs. In-band SQL uses the same communication channel to launch the attack and extract the data. Out-of-band extracts the stolen data via a different channel.
And inferential or blind SQL is fascinating.
It really is. The attacker asks the database a series of true-false questions and infers the restricted data based on how the server responds. The primary way developers prevent all of this is by using prepared statements.
At what point does human psychology become the most critical yet completely unpatchable layer of our network models?
That might be the hardest vulnerability to manage of all.
Until next time, keep diving deep.